Hello, my name is Duncan Lorimer. I'm a professor of physics and astronomy here at West Virginia University, WVU. I've been here since 2006. I'd like to tell you the story of the discovery of a new astronomical phenomenon, fast radio bursts, found at WVU by one of our undergraduates, David Narkovic, in 2007. Fast radio bursts, or FRBs for short, are characterized by a radio pulse that lasts only a few milliseconds and appears to come from random patches on the sky. Although their origin is still very much a mystery, FRBs hold great promise as insightful probes of the large-scale structure of the universe. Okay, so here we see the Parkes 64-meter radio telescope, and it's going to feature prominently in this story. The telescope is pictured in front of a radio image showing our galaxy, the Milky Way. An FRB is shown here as the bright flash, and for a brief period that's going to greatly outshine the rest of this radio sky. Since their discovery in 2007, only about 20 FRBs have been found. Now, it was initially thought that these are strictly one-off phenomena, but as we're going to see, one of these bursts has been seen to repeat. The sporadic nature of FRBs and the relatively narrow fields of view of radio telescopes makes them difficult to detect, in spite of their brightness. When you consider all these factors as a whole, the sky coverage so far and the time spent looking, you come up with an amazing inference. That is that the rate of FRBs over the whole sky could be as large as a few thousand events per day. Modern astrophysics is currently undergoing something of a revolution. FRBs are an example of a class of sources in a landscape that's now referred to as time-domain astrophysics. As technology has advanced and we've been able to study the sky with finer and finer temporal detail, we've uncovered a rich diversity of sources which vary on timescales from days to hours down to milliseconds or less. So, when we think about the universe, both in terms of its regular inhabitants, the sources we see from night to night, as shown here, and now in terms of transient sources, which provide an ever-changing backdrop that's rich in possibilities for future study. You'll also notice in this image the band of the Milky Way, as well as two relatively nearby galaxies, the large and the small Magellanic Clouds. These beautiful objects feature later on in our story. The audio you're now hearing represents the background hiss as collected by the Parkes radio telescope. The FRBs, which can be heard as chirps on top of this background, are depicted in the image as well. The high and low frequencies that are audible here correspond to the radio frequencies which we receive the bursts. As we'll see, this sweeping in frequency is providing clues as to how far away these sources are. It's remarkable that, roughly speaking, an FRB goes off somewhere on the sky once every 30 seconds. The story of FRBs really begins with the serendipitous discovery of pulsars by Jocelyn Bell and Anthony Hewish in 1967. Pulsars represent another kind of transient astrophysical source phenomenon, and as you can see here, are characterized by short-duration pulses which are extremely regularly spaced. These pulses are of widths of a few tens of milliseconds. The telescope that was used to make this discovery operated in the low part of the FM band. Jocelyn and her colleagues looked at the sky with this telescope using pen chart recorders. These devices measured the variations of the radio signals from the sky with time. Now, Jocelyn and that team collected miles and miles of these recordings as they surveyed the sky each week. One of the early observations of a pulsar found using this equipment is shown here. The team spent many months ruling out sources of locally generated interference and other aspects in their observations, and their final analysis that culminated with the discovery of pulsars was published in 1968. As you can see from the abstract of this paper, they concluded that pulsars were entirely new astronomical sources that originated from within our galaxy, the Milky Way. Just from the short duration of the pulses alone, the authors concluded that the sources must have been something like a compact star, most likely either a white dwarf or a neutron star. Now today, the currently accepted picture of a pulsar is that it is a rapidly rotating, highly magnetized neutron star. Such a neutron star formed, we think, from the collapse of the core of a normal star after it underwent a supernova explosion. The pulses that we detect today here on the Earth are produced due to the rotation of the magnetic field as it sweeps past our line of sight. Scientists have been looking for pulsars ever since this discovery, and over the past 50 years have employed more and more sophisticated algorithms to find weaker and weaker pulses, which can't be seen individually. However, it's always been known that pulsars and other compact objects, which might emit bright single pulses, could be seen out to very large distances. So here, we're looking at a picture of the Crab Nebula. The Crab is an expanding shell of gas, which is the remnant of a supernova explosion witnessed on Earth in the year 1054 AD. The nebula itself contains a well-studied pulsar which is spinning 33 times a second on its own rotation axis. Pulses from the Crab have been superposed on the image that you can see here. Most of the pulses, in fact, are actually buried in the noise that you see. What we are looking at above the noise are so-called giant pulses. And these giant pulses can be even hundreds or thousands of times brighter than the mean. So bright, in fact, that such pulsars could easily be visible with current telescopes, even if they were at a distance of a few 100 million light years. That's a much greater distance scale than the Milky Way, which is only a few 100,000 light years across. The promise of detecting pulses from crab-like pulsars and other emitters has inspired a number of searches over the years. In the late 1970s, Stephen Hawking predicted that black holes formed early in the universe's history would actually be evaporating today and be a potential population of sources emitting bright electromagnetic pulses. Inspired by this, Finney and Taylor carried out a search for bursts in data taken with the Arecibo radio telescope. Joe Taylor, subsequently, was a co-recipient of the Nobel Prize in Physics. Still, Finney is now a well-respected astrophysics professor at Caltech. Back at this time, Finney was a high school student working with Taylor. Their search was one of the first of its kind, specifically to look for energetic pulses coming from well beyond the Milky Way. Although unsuccessful, it nevertheless placed the first meaningful constraints on the rates of putative bursting radio sources in the universe. Other searches have been carried out over the intervening years, but despite a few false alarms, no further pulses were found. By the end of the 1990s, as telescope instrumentation and the availability of high-speed computing resources improved substantially over technology from the 1970s and 80s, new interest in searching for radio pulses came. Jim Cordes and Maura McLaughlin at Cornell University were two key proponents of this resurgence, and their papers at the beginning of this millennium on single-pulse search techniques led to a good deal of success over the past decade and a half. On a personal note, the study of pulsars and mysterious transients allowed me and Maura to meet, fall in love, and get married around that time. Maura and I then moved to Manchester University in the early 2000s to take up postdoctoral positions there and began to apply the single-pulse search techniques to data sets from Parkes. The advanced sensitivity of these searches over previous ones allowed us to detect a whole new population of single-pulse emitting sources. One example of these new radio sources, known as rotating radio transients, or RATs for short, are shown here. We see the pulse arriving from each source around the telescope's receiver, which in this case spans a 300 MHz band centered around 1400 MHz. So now we're going to discuss about the radio pulses from the pulsars and how they traverse the space between us here at the telescope and the pulsars themselves. The pulses on their way to the Earth have crossed through what we call the interstellar medium. The interstellar medium is not completely empty, it's almost the perfect vacuum, but it has free electrons in it. Those free electrons have come from young stars, supernovae, things like that, And we talk about a number in the interstellar medium. It's called the free electron number density. It's the number of electrons per unit volume. In this case, 0.03 electrons per cubic centimeter. So that might seem like a very small number, but it has a profound impact on these pulses as they traverse the interstellar medium. So let's start with the pulsar over here. It's spinning about its axis that's shown vertically here as omega. It has a spin period p, which is 2 pi divided by omega. And those pulses, as I just mentioned, are traversing the interstellar medium. Now the key point here is that the pulses are not all traveling at the same speed. The highest frequency pulses arrive at the telescope earlier, and when you plot a graph of frequency versus time, the pulses arrive like this, so that the highest frequencies that we observe come to the telescope first compared to the lowest frequencies. And so what's happening there is that the speed of the propagation of the waves is different, and it's related to the index of refraction, shown here as mu. And there's a rather complicated expression involving the number density of free electrons, the charge on the electron, pi, the mass of the electron, and the observing frequency itself. And you can see there that the index of refraction depends inversely on the square of the frequency, such that the speed of those highest frequency radio waves is faster than the low frequency ones, and they arrive first at the telescope. And that's the origin of this dispersion effect that we're seeing in pulsars and fast radio bursts. In 2006, Maura and I moved to WVU to begin jobs in what is now the Department of Physics and Astronomy. As incoming assistant professors, in addition to developing new astronomy curriculum at WVU, our task research-wise was to hit the ground running and get students working on projects. One interesting idea we had was to search the Magellanic Clouds for rats. We were aware of a paper at that time from Parkes, where the authors had found over a dozen pulsars, but they had not carried out a search for single pulses. The survey had a novel feature in that the data were collected using a so-called multi-beam receiver, shown here. This is a bit like the radio astronomer's equivalent of a multi-pixel camera. Although it has only 13 pixels, or beams as they're known here, each one can look at a different patch of the sky. The receiver greatly increases the efficiency of the telescope, allowing it to look in 13 places at once, and therefore cover over 10 times as much sky in a different amount of time as a single receiver. The image on the sky shows the hexagonal footprint of the multi-beam receiver. The large and small Magellanic Clouds were covered using an interlocking series of these pointings, as shown here. So, with a copy of the data in hand, and with the help of an undergraduate physics major, David Narkovic, we set to work on developing a single pulse search pipeline that would look for dispersed pulses coming from the Magellanic Clouds. The pipeline we used is shown schematically here. Our task is to look for a pulse in the data with an unknown dispersive delay. A segment of raw data is shown here as different frequency channels recording data streams from the sky. A dispersed pulse would roughly follow the diagonal line shown in this graphic. To find it, we need to de-disperse the data for a wide range of delays, which correspond to different dispersion measures, or DMs. Since the DM is equal to the average density of electrons along the line of sight, multiplied by the distance to the source, astronomers quote DMs in rather funny units. Centimeters to the -3 parsecs. So usually, when astronomers talk to each other about DM, they drop the unit and just quote the number. Based on what we now know about the density of electrons in the Milky Way, as a rough rule of thumb for pulsars and rats in our galaxy, a DM of 30 corresponds to about 1 kiloparsec, or 3,000 light years away from the Earth. In our search of the Magellanic Clouds, we looked at DMs up to 500. This estimate takes into account the delay from electrons in our galaxy. in the space between the Milky Way and the Magellanic Clouds, and in the Magellanic Clouds themselves. Pulsars in the Magellanic Clouds only have a DM of up to about 260. I also added a little bit of extra DM headroom into the search, simply because I didn't feel like I knew what to expect well enough. This turned out to be a fortunate choice, as we'll see in a moment. For each DM value, we produce what we call a time series, a graph of intensity versus time, as shown here. In these time series, we search for peaks that are significantly above the background noise level. The results of this search are shown in the bottom plot, which gives dispersion measure versus time. The bigger the point in this diagram, the brighter the pulse. In this example, a known test pulsar has been passed through the pipeline, and pulses from it are seen as the horizontal band along the center of the image. Other bright pulses at low DM are seen at the bottom of this graph. These are due to sources of interference. David would come and meet with me each week to show me what he'd been up to. I remember on one occasion he showed me a particularly interesting plot seen here, which shows the results of our search for one of the observations of the Small Magellanic Cloud. Apart from the low dispersion interference on the lower right, what's really striking in this plot is the highly localized event that was detected about half an hour into the observation. I remember not really knowing what to make of this event at all. The DM of this event was 375. This was well above the value I was expecting for the Magellanic Clouds. But the position of the event on the sky shows that the pointing was in fact a degree away from the Magellanic Clouds. We were really not expecting to see anything with this DM in this location at all. So being somewhat shocked by this detection, and not really knowing what to do next, I told David to keep looking through the rest of the data to see if he could find more examples of signals like this one. Well, despite a few more weeks of careful searching, David found nothing else, no other events, and we were left with this one anomalous pulse from the survey. Shortly after that, I was on another observing trip to Parkes, talking to one of my former postgraduate advisors, a good friend of mine, Matthew Bales. So Matthew and I sat down and we made a plot like the one you're looking at here. This type of plot is similar to those examples from the rat pulses that we saw earlier. As you can see, this burst really is a textbook case. It shows the dispersion delay of arrival time with frequency. The white lines that you see here that are flanking the pulse are overlaid here simply to guide the eye to depict how a pulse with this dispersion measure would appear at the telescope. If you look closely, you'll also notice that the pulse gets broader with lower frequencies. This is a hallmark that we expect for pulses propagating through a turbulent medium, and it's well known from studies of pulsars that we've done over many years. Over the coming few months, carrying out a number of checks and follow-up observations, we became extremely convinced that this pulse was real, and wrote up the results of our detection in an article to Science, which appeared in August 2007. As we boldly claimed in the abstract of the paper, despite it being only a single detection, all the available evidence pointed this to being a prototype of an entirely new source population. Its anomalously high dispersion led us to estimate that the burst was as far as a few billion light-years away, and perhaps representative of some catastrophic explosion in the distant universe. Making parallels with gamma-ray bursts, a similarly enigmatic population of sources that had been known since the late 1960s, we speculated that the rate of these new radio bursts over the sky could easily be as large as a few hundred per day. Among the predictions we made is that other bursts should be present in existing archival radio data sets. A number of groups began to look for these. About a year after the discovery paper came out, I was back at Parkes observing for another project. I got a call from Matthew Bales. Matthew told me about some upcoming work that his student, Sarah Burks-Belair, had been doing. Sarah had indeed found more bursts, and these shared some properties with the original one that we found, but with one important and worrisome difference. The newly detected bursts were consistently seen in all 13 beams of the receiver. That is not supposed to happen for real astronomical sources, which are incoming plane waves brought to a focus by the dish and are typically seen only in one beam, or perhaps a few neighboring beams if they're really bright. Here, the implication is that we're seeing a signal that has got into the receiver from a different path, and most likely some local source of interference. So even though at the time the origin of these signals was not known, it was clear to Sarah and Matthew that these bursts were really not of celestial origin, and they were dubbed peritons, after the mythical Greek elk that casts a human shadow. The implication with this name is that the peritons are locally generated signals masquerading as something astronomical. The worrisome part was that the delay exhibited by the bursts looked a lot like the original Lorimer burst that we'd found. By this time it had inherited my name. So the multi-million-dollar question was whether the Lorimer burst was a periton as well. On one hand, it was seen in only 3 of the 13 beams, which argued for a celestial origin. But on the other hand, its delay with frequency was eerily similar to the peritons. Questions were naturally raised, and doubts began to set in. I myself was beginning to have second thoughts. What kept my hopes up was that the structure of the original burst in the frequency time plots was also quite different to the peritons. As you can imagine, these were really troubling times. People used to ask me whether I still believed in the burst's validity. To make matters worse, even my own wife began to doubt me. Here's a paper that Maura put out in 2011 with some colleagues where they found more examples of peritons and asked the reasonable question shown here. Paraphrasing this essentially amounts to the question: if the Lorimer burst is really a prototype of a population of sources, where are the other examples of that population? It's a reasonable question, you must admit.
So I got my PhD at Cornell, and part of my thesis research was developing software that would detect isolated radio bursts in data from large radio telescopes. I applied that to a couple radio searches as a PhD student, and I didn't find anything, which was pretty disappointing. Then I went to the Jodrell Bank Observatory as a postdoc, and I got involved in a survey called the Parkes Multi-Beam Pulsar Survey. And this was a survey for pulsars with the Parkes telescope in Australia. And I decided to apply this code that I developed as a grad student to the data from this Parkes survey. And that was really exciting because we found a whole new class of sources, a class of neutron stars that were only detectable through their bright radio bursts. And we called these things rats, for rotating radio transients. And so I wrote this paper on these rats, and then we decided, it would be fun to apply this same kind of search algorithm to lots of different types of data. And one of the data sets that we looked at was data taken of the Small Magellanic Cloud, and that would be the survey that this fast radio burst was detected in. The first summer that Duncan and I were here at WVU, it was the summer of 2006, we had an undergraduate student named David Narkovic working for us, and he was looking at radio data taken on the Small Magellanic Cloud, which is a satellite galaxy to the Milky Way. And he was applying this pulsar search software that I'd wrote that looked for these individual radio bursts to the data from this Small Magellanic Cloud. And one day he came to Dunk's office with a plot which showed the detection of a single burst, which was at a very high dispersion measure, which means a very far away distance. It was coming from like really far away. And my first reaction when I saw the plot actually wasn't super excited. I looked at it and I just said, oh, that can't be real. Like, there's no way we could be detecting a pulse from that far away that was that bright, because it was really bright too. So I sort of sent David away and said, this can't be real. It's not, astrophysical. Figure out what it is. It must be some kind of radio frequency interference. Dunk was much more optimistic than I was, and he was really excited about it. And in the end, of course, he was right, and it did end up being an astrophysical source. But soon after David found the burst, we looked into it in a lot more detail, and it ended up having every single property agree with what we'd expect from an actual astrophysical source. So then I kind of came around, and I was really excited too. It looked like this thing was real. It looked like it was a pulse from another galaxy. And we thought, wow, we're going to find lots more of these when we look at way more data with this search algorithm. However, we looked at data from that survey and another survey and another survey, and we didn't find anything else. We never saw a single other thing like this for about 2 or 3 years after the original discovery. So I started to have doubts, and I thought maybe this thing isn't real, because if it's real, there should be a whole population of these things out there, and we didn't see anything else. And then in 2010, there was a paper published by another group of researchers where they announced the discovery of a new source of radio frequency interference, of man-made radio signals at the Parkes telescope. And these human-made signals really looked an awful lot like our astrophysical burst. So that really gave me even greater doubts about the nature of the original burst. It seemed like we should have seen more of them if it was real. And they also looked really similar to these other things, which were called peritons, and which were definitely not astrophysical. So the mood back at home was pretty interesting in those years after the initial burst detection. I would say that Dunk never questioned the astrophysical nature of the original burst. He really believed it was real. I would say that I was a little more skeptical. So when this paper about these peritons came out, I honestly didn't know what to think. I had also done other surveys. I looked through this entire Pulsar survey, a really large amount of data, and didn't find a single other one of these bursts. And I actually wrote a paper along with an undergraduate student and a postdoc here at WVU that actually concluded that these bursts probably were not real, or else we would have found more of them in the data set that we looked at. And so the mood was a little bit tense because Dunk really believed it was astrophysical. I questioned it, but I would say it was not unpleasant. It was kind of, it's always fun to have a bet with someone you work with, and even better with your husband. And so we were both just like really curious to see who would end up being right, because we knew that eventually we'd get to the bottom of it, and either there would be lots more of these things found, or never another, and one of us would be right in the end. If I could go back in time to 2006, when Dunk and I first discovered this original burst, I would do things differently. Now that I know that there's a whole population of these things and they are real, I would have spent a lot more time searching for them in the late 2000s. And in fact, I think both of us probably would have made this like the cornerstone of our research program. We would have got lots of students, postdocs, undergraduates involved in carrying out searches. We would have built new types of radio telescope arrays that were like really optimally designed to detect these kind of things. And unfortunately, because we weren't really sure whether they were real, and furthermore, the community was not really sure and didn't want to fund us to do this work, things really got pushed back a long time until another group found 4 of these with the Parkes telescope in 2011. So there was a really big gap between the initial discovery and when more of these were found. That sort of allowed the field to grow.
Fortunately, we didn't have to wait too much longer for more bursts to be found. In 2012, Evan Keane and his collaborators in the UK and Germany published their detection of another burst in archival data. This one was seen in only one of the beams of the receiver and had a completely different delay. The burst was taken in data from a survey of the Milky Way, and therefore in a completely different direction on the sky. Much like the Lorimer burst, however, its dispersion measure was larger than that expected from electrons in the Milky Way. So, it too appeared to be coming from much further away than the galaxy itself. More bursts from this putative population were to follow in a paper by Dan Thornton and colleagues in 2013. I'd heard rumours of their discovery in late 2012, and so eagerly awaited the paper announcing 4 more bursts with different DMs and positions. As you can see on the figure, when the DMs are graphed against galactic latitude, they are clearly anomalous compared to the DMs of the pulsars in the galaxy. Things were looking up again. Finally, a population of sources had been found, and with a new population, it's always the fun part of naming them. What should this population be called? Lorimer bursts? That seemed a little bit much, even for me. Sparkers? Maybe, a bit colloquial perhaps. Fast radio transients, or FARTS. I don't think that would ever fly, do you? Instead, fast radio bursts, or FRBs, was adopted by Thornton et al. We name individual FRBs after the year, month and date at which they arrived at the telescope. For example, the FRB discovered on February 20th, 2011 is called FRB 110220. All right, so now we're going to talk about fast radio bursts in the context of the expanding universe. And one thing that we learnt back in the last century, Edwin Hubble taught us that the universe is not a static entity, it's in fact expanding. All the stars and the galaxies are receding from one another, such that when you have a distant object like a fast radio burst, when it is emitted from its host, shown here as a little blob with an H in it, that's probably some sort of galaxy far away, it has a characteristic wavelength, lambda emit, shown here as the distance between two wave crests. And that pulse ultimately will arrive at the Earth, but it takes a long time for it to get here, billions of years in some cases. And over that timescale of billions of years, the whole universe has expanded, such that it's changed its characteristic size. Let's say when the pulse was emitted, the characteristic size was d emit up there. And by the time that the pulse has arrived at the Earth over here, billions of years later, the universe has expanded such that its characteristic size is d obs. And correspondingly, its wavelength has been stretched by that expansion, such that the observed wavelength, shown here as lambda obs, is fundamentally greater than the emitted wavelength. So we can express that difference in what astronomers call the redshift, and that's shown here. It's the fractional increase in the wavelength. So you can see as it's written, it's lambda observed minus lambda emitted divided by lambda emitted. And if you look at that for a second, you see that you've got lambda observed divided by lambda emitted, and then lambda emitted divided by lambda emitted. So that's just 1, that part of it. So we can move that 1 over to the left-hand side and rewrite it a little bit. And so we get 1 plus z, which is what we call the redshift, the quantity z, is just equal to lambda obs divided by lambda emit. And so that's a very fundamental formula for astronomers. Let's think about what it means for a second. If I have a redshift of 0, so I put z equal to 0 here, that means I just get 1 on the left-hand side. What that means is that lambda obs is equal to lambda emitted. And so physically what's happened, the source is so close that the expansion of the universe has been insignificant over that time. So these are nearby sources. So I'll just put redshift of 0 is local. We suspect, with good evidence now, that fast radio bursts are observable all the way up to redshift of 1 and perhaps beyond. Let's think about a redshift of 1 burst for a second. So if I put redshift of 1 here, then if I look in my formula up here, I've got 1 plus 1 equals 2. And so what that means is that the observed wavelength is twice as large as the emitted wavelength. And we call these types of sources cosmological. I'll just abbreviate it there. Those are cosmological sources. Fundamentally, in terms of the expanding universe, what that means, because the emitted, the size scale of the universe when the pulse was emitted is so much shorter than the size scale of the universe from when the pulse was observed, because those are attached to the wavelengths of the observed and the emitted pulses. You can also write that this is equal to d obs over d emit. And so my source at redshift 1 occurs when the universe was half of its current size. So the pulse was emitted when the the universe was half of its current size, roughly half of its current age. So that's a very brief introduction to cosmology and why it's important for fast radio bursts. Despite having found a population of sources and winning over many doubters from the community as to the validity of the bursts, there were still some concerns as to why FRBs were seen only with Parkes. Was it perhaps some still bizarre form of interference only detectable at Parkes? The actual reason was much less sinister and merely a result of the fact that out of all the large telescopes that could detect FRBs, Parkes had been spending a lot more time on sky compared to other observatories. This is still very much the case, but in 2014 and 2015, the balance had begun to be redressed somewhat with the discovery of FRBs at the 305-meter radio telescope in Arecibo, Puerto Rico, and the 100-meter Robert C. Byrd radio telescope at the Green Bank Observatory here in West Virginia. In addition to their verifying that FRBs were really a celestial phenomenon, these two bursts that are shown here are notable for the fact that the Arecibo one repeats. We'll talk more about this later. And that the Green Bank burst was the first one detected at radio frequencies below gigahertz. So, as we mentioned earlier, the fact that the peritons were seen in all 13 beams of the Parkes receiver indicated that they really had to be local in origin. But it wasn't until 2015 that the source of these signals was tracked down. It turned out to be due to microwave ovens in the Parkes Visitor Center. Now, by this time, a significant amount of effort had gone into the development of technology that was able to detect bursts at the telescope in real time. The early discoveries which we made in archival data were not seen until analyses were carried out months or even years after the signal had arrived at the telescope. In Matthew Bale's group at Swinburne, a lot of development had been carried out that led to the development of a new real-time system that was in use by 2015. Upon the suggestion of a microwave engineer, the team at Parkes, led by then PhD student Emily Petrov, set about tracking down the source of the signals. They discovered that they were produced exactly at the moment that a microwave door is opened while the oven is still carrying out its cycle. Now, you know that feeling when you're microwaving a drink or a snack and you just can't wait any longer to get your hands on it? You open the door of the oven while the microwave is still running. In that brief instant, a spinning magnetic device which is inside the oven that's producing the microwaves begins to slow down. Its rotation frequency produces a chirped pulse in the radio band, and because the door of the microwave oven is open, the signal leaks out. Parkes and other large radio telescopes are so sensitive that they can pick up these signals even when the dish is pointing in a completely different direction. To further emphasize this result, we're showing here a histogram that gives you the incidence of peritons plotted against time of day. As you can see, the peritons are most commonly seen around lunchtime, local Australia time. Very importantly, the rest of the FRBs show no preference for lunchtime at all. The Lorimer burst, which we detected, turned out to be at a time in the early hours of the morning when the visitor center was closed and the microwaves were definitely turned off. So up to this point, we've talked very little about what FRBs could be. This is really because we don't yet know what they are. Those theories that have been put forward so far explain FRBs in three main categories: extraterrestrials, galactic sources, or extragalactic sources. The first of these scenarios, that is that FRBs represent some sort of message coming from ET, that can largely be discounted simply from the preponderance of the FRBs over the whole sky. Indeed, similar arguments were made following the discovery of pulsars 50 years ago. Any source of FRBs that originates in the second category, that is as natural sources of radiation from within our galaxy, the Milky Way, this category has to find a way of explaining the extremely high DMs that we're observing for FRBs, particularly when you compare that to the pulsar population that's now well studied in the galaxy. And despite some attempts to explain the anomalous dispersion coming from flare stars, This option remains less attractive than the final scenario, that is, the extragalactic scenario. Clearly, that's setting the distance scale for most of the currently viable theories that exist. Within this category alone, there are currently more theories proposed than bursts actually known. Let's look at some of those that are suggested. Collapsing neutron stars forming black holes is one category. Several scenarios involve coalescing sources due to gravitational radiation, coalescing neutron star binaries, coalescing neutron star black hole binaries, coalescing white dwarf binaries, are all different variants on the same thing. We can also have comets falling onto neutron stars, black holes evaporating, giant pulses from young neutron stars, or giant flares from highly magnetized neutron stars, the so-called magnetars. Supernova explosions, and even white holes have been speculated among these various scenarios. My personal favorite is the giant pulse model from those young neutron stars. As we mentioned right at the start of this story, these pulses have been observed in the Milky Way. And in that sense, it's a known emission mechanism that we can extrapolate further. The giant pulsing model, in this sense, has a clear prediction. That is, that all FRBs will repeat if we observe for long enough. Now, while this model and all the above scenarios involve compact stars, neutron stars, white dwarfs, or black holes, there are a number of non-stellar objects, non-stellar options involving dark matter and cosmic strings that have also been proposed. Cosmic strings are large-scale defects in the structure of space-time. These are thought to have been formed in the universe's early inflationary history. FRBs are produced when such strings interact. Now, this is very speculative, but the very fact that these theories are viable at the current time tells us really that much is to be learned about FRBs. So to conclude, we now have a population of mysterious radio bursts that are currently of unknown origin. They appear to come from random locations on the sky. Perhaps the most remarkable thing about them is their inferred rate of occurrence. Somewhere over the sky, an FRB goes off about once every 30 seconds. Now, although all the models we've reviewed can be tuned to accommodate this rate, many of them could actually be ruled out if we knew the distance scale for FRBs, and hence get their rate per unit volume in the universe. Just to emphasize the extent of the problem that we have with the rate, it's worth noting that FRBs are currently not too far below the most violent known explosions in the universe, supernova explosions. Supernovae occur something like a rate of about once per second somewhere in the universe. Now, if we're missing a significant fraction of faint FRBs, let's say, or if many of the FRBs that we're seeing, many of them are not even beamed towards us, the rate that we're currently inferring could be as high or even higher than the supernova rate, and that could produce potentially a large problem. Are there multiple populations of these bursts, those which repeat and those that do not? Really, only through the discovery of a larger sample of these objects will we actually be able to answer these questions. Right now, new FRBs are continuing to be found with existing instrumentation. Very recently, a team led by Vikram Ravi at Parkes has announced the discovery of a spectacularly bright FRB. The properties of this burst potentially allow us to constrain the magnetic field within the cosmic web. That brings the question, even if we don't fully understand what FRBs actually are, studying them in large numbers just by themselves looks set to provide valuable insights into the large-scale structure of the universe. Fortunately, the next 5 years is set to be very promising for FRB hunting. New instruments that are coming online right now at Arecibo, Green Bank and elsewhere, they really promise to find more of these enigmatic sources. Most notably, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, is now set to begin operations in 2017. That looks set to detect FRBs at a rate of dozens per day. So, A new giant telescope in China, known as FAST, the 500-meter aperture spherical telescope, has also recently been completed. That telescope will have unprecedented sensitivity for faint and distant FRBs. Another new facility in South Africa, known as MeerKAT, will soon begin scanning the skies for FRBs, and it has an optical partner known as MeerLicht, which will simultaneously observe them at optical wavelengths. MeerKAT itself is a precursor to the next generation radio telescope. That's known as the Square Kilometre Array, or SKA. The Square Kilometre Array, upon completion in the mid-2020s, would be able to locate and study FRBs to unprecedented precision. There's really no doubt that there'll be many surprises in store as we enter the second decade of study of FRBs. I'll boldly predict right now that by 2030, around the time of my retirement, FRBs could become standard tools to study the cosmos. Now, only time will tell, of course, if that prediction's correct. But if the first 10 years is anything to go by, FRBs will be presenting us with a lot of surprises over the next decade.